Hello, we are Team 84, or the Trash Collection Rover team. This is us in the lab, if you have forgotten what we look like. I am Michael Sampanato. I'm a computer engineer here. My main subsystems for the rover are image recognition and pathfinding.
I am Cameron McGugan. I am in electrical engineering, and my two subsystems are power and drive motors.
I'm Thomas Crocker. I'm electrical engineering, and my two main subsystems are the chassis and the claw.
For our design requirements, unfortunately, we had some parts that weren't able to come in on time, so we weren't able to completely demonstrate everything. There were some that we were able to demonstrate fully, and some that we aren't. So the rover design should be able to scale in size with minimal effort. The rover should be able to fit in a 24-inch cube, and the rover should be able to connect to an external server over Wi-Fi. All of those will be able to be shown. The rover should be able to move up and down 20-degree inclines and make 90-degree turns. The rover should be able to sense and avoid obstacles, and the rover should have GPS capabilities to limit its searchable area. All of these are implemented, they just weren't able to be completely demonstrated due to lack of parts. And then the rover should be able to pick up and store trash up to the size of a 12-ounce can, and the rover should be able to run on an 8 amp hour battery. Again, with these, either the design requirements have changed a little for the midterm demo, or we do not have the parts that are needed for the power system. And so next I will be introducing the subsystem. Hello, I am Cameron. The subsystems I had were the power and motor subsystems. Unfortunately, we didn't have the parts come in time for any of my subsystems to really be demonstrated properly. So instead we have schematics as well as rationalization of why we know our circuits will work. So the first thing we did was the battery charging circuit. How this works is we'll take 120 volts AC coming in and drop it down to 18 volts DC, where we'll use an LM317 to provide the constant current followed by constant voltage followed by the float charge necessary to charge our 12 volt 8 amp hour lead acid battery. And we also have a 2 amp fuse there to get rid of any overcurrent that might happen. Next thing in the circuit we'll have is the low battery indicator and shutoff. We'll use the LTC2960 supervisor, and what it'll do is it'll indicate us when the battery reaches 11 volts and then shut down everything gracefully once the battery reaches 10.8 volts. The data sheet can be seen right here. We pretty much just use the base model given to us for what we need to do to get the circuit to work. The only thing we needed to change were a few values to get it to the correct voltage we need for it to indicate to us. And so that should work as expected. Next part of the circuit we had was the 12 volt buck boost converter. Lead acid batteries go anywhere from 13 volts to 11 volts. So because of that, our motors take 12 volts, so we need 12 volt output. So this allows us to do 12 volt output up to 10 amps. This once again was given to us through the Linear Technology Corporation. The layout we need, all I needed to do was calculate the different R-sense and R1 and R2 in order to get the proper voltage output we needed. The next section I have is all of our buck converters. So we have a 5 volt buck converter, a 10 volt buck converter, a 3.3 volt buck converter, and a 1.8 volt buck converter. So the 5 volt buck converter allows for 4 amp output. That's to power our microcontrollers as well as the camera module. The 10 volt buck converter is for the stepper motors for whenever we decide to add that to our subsystem. The 3.3 volt buck converter that powers the ESP32, as well as some extra power rails for the Raspberry Pi compute module, and then the 1.8 volt buck converter, which again powers the Raspberry Pi compute module. And we can see the data sheets right here. Texas Instruments is very nice to provide us the necessary values as well as the layout for what we need. So we know that these should work as expected. So here is the LMR 33640, which should do 5 volts at 4 amps. We have the LMR 33620. This will allow us to do 10 volt output at up to 2 amps, as each stepper motor only takes 500 milliamps, followed by the TPS 56339, and this will do this will do our 3.3 volts at an output of up to 3 amps. And then we have our TPS 56120, which will output our 1.8 volts and add up to 1 amp for our Raspberry Pi compute module. Next we'll be showing the motor drivers. This is the schematic we used for the motor drivers. We were lucky enough to have Toshiba send us some evaluation boards so that way we can test and make sure they work before our chips showed up. So we were able to demonstrate this one. These were the circuits used. And we'll be using them in large mode so that way we can have up to 8 amps output per motor. And in the next video you see, you will see the motors actually running.
So for the body of our rover, we have the bottom made out of maker beams and the top, which is flipped over right now, made out of plywood. The motors will sit on this shelf right here and be connected to our continuous tracks that are not attached right now. And then we have 2 idler wheels that will be running along the tracks as well. So as you can see, the tracks are connected. The motor would be right here, sitting on this shelf, and it would be connected to our drive wheel, which would be propelling the motor. So as you can see, it can go back and forth pretty easily. We also have a requirement that it holds up to 7.5 kilograms. I have 17.5 pounds, about 8 kilograms. And as you can see, it holds pretty well and can still move.
So this is the block diagram for the gantry system. So first we'll have an energy decoder send information to our gantry controller. The gantry controller will control the stepper motor, which will move the arm along the x-axis. Once it gets to its spot, it'll lower in the y-axis by a chain. The gantry claw will reach the ground, and another stepper motor will pick up the trash and then raise it back up and move it to the bins. This is a schematic for the motor driver that controls the stepper motor, and this is what will run the gantry system.
Currently with real-time object detection, we unfortunately are delayed due to no camera being delivered to me. This is once again just due to delayed deliveries that correspond with COVID. However, I can show you the neural network running on still images such as this one. There is a single problem so far with my neural network. It's been trained on YOLO v4 and it's been training for a couple of days. The problem is that my data set that I used had misannotated cans, and if you know anything about neural networks, or rather model training, the data that you use to train it is as important as any other math. So having misannotated images resulted in it being unable to identify things that it should, such as this can and even these chairs and this cooler. This isn't a huge deal. I just have to fix that data set and then retrain it on a fixed data set. But once again, without a camera, I can't show you it in real time, which is very unfortunate. I wish I could. But moving on to pathfinding.